So why is the name cast iron? Cast, you know, right? Casting. You have the molten metal. You put into some mold, and then you have the things or the material that you want. And actually, this the name it implies that we don't intend to shape the material anymore. Okay, for the steel, then we have rolling, forging, drawing. We put some work or shaping to the material. But for cast iron, whatever we cast, that's it. Because it is very hard and it is very almost not possible to shape it by rolling or forging and so on. And to do cold work, even hot work is not favorable. Okay, so the content is around 2 to 4% carbon, and also at the same time we do have silicon inside the alloy. So other alloying element may also present to control or vary certain properties. So that is some freedom of the alloying element lah. And based on that, we will have different products of cast iron. But the family is cast iron. All right. So if we take a look on the phase diagram, so here is the steel. This side is the steel. Okay. And we look at this right hand side. Right. Okay. And if we take a closer look on this part. So at first we want to understand the solidification of the cast iron, how it is different from the steel, right? So if you remember the steel, we talk about this austenite phase. We talk about a lot about the austenite phase and this ferrite and pearlite. This is eutectoid, from one solid into two kind of solid. What is that? The ferrite and cementite. And at this eutectoid, this ferrite and cementite, it form lamellar structure, and that is what we call the pearlite. So that is for the steel. And how about for the cast iron? Okay, so cast iron, we focus on this red area, for example. So steel, okay, has a pearlitic base microstructure, okay, steel, and cast iron has a ladyberitic base microstructure. Okay, so this pearlitic came from this eutectoid point. Okay, but this ladyberitic, it came from this point, which is eutectic. So what is the difference between eutectoid and eutectic? Eutectoid, we have one solid into two kind of solid. But for eutectic, we have liquid into two kind of solid, right? So this is solid to two kind of solid. This is liquid to two kind of solid. So that is eutectic. Eutectic. So eutectic is at 4.3. So what you got from the eutectic point, we got uh, the austenite and also the cementite. Okay, we have the austenite and cementite. E3C plus austenite. Okay. We got austenite and cementite. So that is what we get. We have at this eutectic point. Okay. And we will further elaborate that afterwards. But we have actually we have four types of cast iron based on the microstructure, based on how it solidify. So we have and based on the composition, we classify four types of cast iron. We classify four types of cast iron: white cast iron, gray cast iron, ductile cast iron, malleable cast iron. So we have four. Okay? And we have a look on each of them. The white cast iron, it contains between 1.8 to 3.6 of carbon, and this is the point, low silicon content. Okay, low silicon content. So you have low silicon content with this amount of carbon, and the white cast iron solidify in rapid cooling rate. Yeah, this is also the rapid cooling rate. And carbon will precipitate as cementites. Okay. Okay. Due to low silicon content. And okay, it received its namesake for its off-white fracture surface color, which results from cementite. Okay. So this is what we will see afterwards. What we need to uh, what we need to dig in is this at first we want to study the microstructure of this white cast iron. Okay, at very high temperature we have the iron, the cast iron in form of liquid, and as it goes down this line, this you have a fixed composition. As the temperature goes down and it passed through this line, partially the solidification start to occur, and we have the liquid plus the austenite. A liquid plus austenite. So partially we have the austenite there, and due to the formation of austenite before or above the eutectic line, this is the eutectic line. Once you cross this eutectic line, you will have eutectic reaction, which is liquid to two form of solid. Okay, but before that, whatever solidified before that, we call it pro-eutectic austenite. Something, the austenite that solidified before eutectic reaction. Okay, so we have this pro-eutectic austenite. Well, this is how it looks like. Okay, how it is illustrated as. Okay, so when we solidify, all right. So this pro-eutectic austenite, it grows as it goes down. So we have some amount of pro-eutectic austenite, and once it um, here we have austenite and also liquid. We have a mixture austenite and liquid. And once the temperature goes down beyond the eutectic temperature, so the remaining liquid which did not transform yet, so the liquid will solidify as two component. One is the austenite. Okay, so this one is pro-eutectic austenite. So you just ignore this one. So you have a eutectic austenite given by this dot, and this blue color is the cementite. The blue color is the cementite. The cementite and austenite. So overall, it looks like this. No? Overall, it looks like this. Okay. We have just now we have the already solidified pro-eutectic austenite, and we have the remaining liquid will form the eutectic austenite and cementite. Okay, and if we go further below, we know that austenite is not the phase which is stable at lower temperature. We have seen that in steel. Okay, dalam steel we have uh, already know about that. We have already know that austenite is not stable at high temperature. So once this is the Eutectoid line 727 that we have been dealing so far. Okay. So we have been dealing with the austenite for quite some time. So when we go beyond this temperature, the existing austenite, it will change into ferrite and cementite, and in lamellar form, so we call it perlite as usual. So you have the perlite and surrounded by the cementite. So that is this structure of eutectic austenite, this pro-eutectic austenite, the cementite, the whole structure is considered as ladyburites. And once it changed from austenite ladyburite to, so the thing is that what's important is that we understand that the microstructure of the white cast iron is how it evolved, and the final product is made up from a lot of cementites. And this cementite, when we, for example, we apply some tensile force, and when it breaks, we learn about that. So when it breaks, so the fracture surface will be mainly of the cementite phase, and that is where we have this color white fracture, and how we get the name white cast iron. And this is how it looks like. This is how it looks like. Okay, the microstructure of S-cast white cast iron contain large amount of iron carbide in eutectic matrix. White cast iron are hard and brittle, alright? Hard and brittle. So the application of white cast iron is used in abrasion resistant part when brittleness is of minimum concern. So we have a cement mixer. So the liner here, the liner, we use all this white cast iron lah. Okay, it's hard. It's hard and brittle. So uh, we don't want something that is structural. I mean, if it is supporting a structure, we don't recommend to use the white cast iron, but we use it, and we have a little concern about the brittleness. So yeah. Uh, okay, we have been dealing so far with the transformation of when we talk about the carbon, usually we always mention the cementite. But actually, for the carbon that dissolve in iron, if the content, if the amount is large enough, number one, and if there is opportunity for diffusion, okay, and in terms of time and temperature, or we can say it's heat or energy for diffusion, if we have these two, so sufficiently, instead of cementite, instead of forming this compound with iron, it it prefer to form on its own kind, with its own kind, and they form what we call as graphite. Okay, and the cast iron, okay, the richer carbon content facilitate graphite precipitation. So, like I said just now, number one, if we have enough amount of carbon, okay, it somehow push the formation instead of cementite towards graphite. Also, addition of high content of silicon will stabilize carbon in form of graphite as opposed to cementite. Okay, and silicon also plays part if we have a large amount, or we have a amount an amount of silicon. It also act as stabilizer for the carbon, and it helps the formation of graphite. So we go to the gray cast iron. Gray cast iron. So yeah, the content is like this. It's slightly higher, the carbon, and it is formed when the carbon in the alloy exceed the amount that can dissolve in austenite and precipitate as graphite flakes. So we know that um, the matrix or the host metal, the solubility has some limitation. You can add, or you can provide a certain amount of alloying element, but at one time the it will be so much saturated, it cannot dissolve in the matrix anymore. It cannot dissolve in the host metal anymore. So it becomes precipitate. And in this case, for the gray cast iron, it cannot dissolve in austenite anymore, and it form graphite flakes. So when as a comparison with the white cast iron, when the gray cast iron is fractured, okay, the surface appear gray because the presence of the graphite. So this is how it gets the name gray cast iron, because there is graphite. Okay, so we take a look on the solidification of gray cast iron. So we have this amount or the composition of this one around 2.3 something, 2.3. And okay, and similarly, we have the liquid in the first place, and then as we pass this line, partially it solidify into austenite, and this is what we call the pro-Eutectic austenite. And as we mentioned just now, the amount of carbon is high. It exceeds the limitation of the solubility in austenite. So it forms graphite. It forms graphite. Of course, there are some carbon which dissolve in the austenite, and because the number is too much, so the carbon, it forms graphite as well. So once it formed graphite, we can say that the amount of carbon in the austenite decreased. The amount of the carbon in the austenite decreased, and the amount of carbon decreased, and we can uh, illustrate that by shifting of the composition. So we have the graphite and the remaining carbon in the austenite. The remaining carbon in the austenite will form cementite. Okay, will form cementite. So as it goes down and it goes down, okay, there will be formation of cementite. There will be formation of cementite, and like this one, just now the white cast iron uh, this one cannot show. Correct. So the white cast iron, we have a lot of cementite. We have a lot of cementite. But for the gray cast iron, we have already how to say, ooze out or squeeze out the carbon, the amount of carbon in form of graphite. So we have a larger amount of austenites, and we do have the cementite. We have the cementite, and as usual, this is eutectic. Okay, this line. As it goes beyond eutectoid line, the remaining austenite will form perlite. So this is how it looks like. This is the flakes that we were talking about, the graphite flakes. And it occurs, compared to the white cast iron, it occurs at a moderate cooling rate. Okay, or slow moderate or slow. So meaning that relatively, the solidification occurs slower. The slower means there is enough time and energy for diffusion to occur. So that is why the carbon it has that opportunity to form with its own kind the graphite, to form the graphite of with its own kind. So that is how the graphite is used. Okay, so if we slow it further, the at moderate cooling rate, from the austenite, it will form the perlite. But if we slow it more, so the carbon inside the austenite also it has that opportunity to get together to form graphite. So the remaining structure will be only ferrite. So we have I think at the end of it we have the microstructure. Yeah, it looks like this now. For the gray. So if fast cooling it become white cast iron, okay, we want become white cast iron. If it is moderate cooling, we have this graphite flakes, and also we have the austenite that will change into the perlite. So we have a perlite and uh, graphite. We have the perlite and the graphite. So yeah, we have this perlite and the graphite. Oh my. So if we conduct a very slow cooling, so when we say the perlite, we have a cementite here, right? So the remaining cementite or the carbon inside the cementite, it have the opportunity to get together to form this graphite or extend the graphite. So the remaining phase left is only ferrite. If it is slow, I mean, yeah, compared to others. Um, so we go back to this is how it looks like graphite flakes. And in moderate, for moderate, it will the final microstructure will be perlite plus graphite. But if we slow enough, if we provide the opportunity for diffusion, the energy and the time, the carbon will form or will get together to form the graphite, and the remaining phase will be only ferrite. So the application of gray cast iron has high strength, and so high melting temperature, very resistant to wear, and has excellent vibrational damping capacity. So we use as the material for engine cylinder block. Because this cylinder block it has it will vibrate and much. So it needs something that have this damping capacity. And the next just now. So we have done about the white iron, gray iron. So we go to the ductile. Okay. We try na, we five long. Later 8:45, 43. We continue. Okay, sorry lah, pagi-pagi buat hal dia punya spek saya terpijak dia patah. So kena dekat sikit tengok. Okay, so kita sambung balik, we continue. You guys okay? Ada ke kat situ? I've been talking for
Ada.
quite some time. Ada. Alright. Alright. So next, just now we have covered the white cast iron and grey cast iron. Now we take a look on ductile cast iron. Ductile cast iron, right? Ductile or nodular? Nodular is something that have node lah, that like have a round shape. So okay, right. The composition of ductile is similar to grey cast iron with respect to carbon and silicon content. So it is similar with grey cast iron by adding small amount of magnesium. So this is the point. Magnesium and okay, by adding small amount of magnesium and or cerium to grey cast iron before casting produces ductile cast iron. Graphite still formed by as nodules or sphere-like particles instead of flakes. So the grey cast iron, the graphite formed in form of flakes, graphite flakes. But for ductile cast iron or nodular cast iron, it form nodules or sphere-like. So how it looks like this macam ni. So all this shape. In ductile iron, graphite is in the form of nodules rather than flakes as in grey iron or grey cast iron. Alright. Moderate cooling rate produces pearlitic ductile cast iron. Slow cooling rate produces ferritic ductile cast iron. So this is this two is the same as what we mentioned for grey cast iron. So if we provide enough, you know that we have this austenite phase. So when we have enough time and diffusion to occur, so the instead of forming the cementite, the remaining carbon in the austenite it diffuse out to combine with the graphite and leaving out only ferrite. If it is a little bit faster or moderate cooling rate, it will form this pearlitic. Pearlitic means there is ferrite and cementite, okay, alternating in lamellar structure. So the application of ductile cast iron, it has good fluidity and castability, excellent machinability, good wear resistance. So it can be machined, it can be a little bit processed lah. Okay, it has machinability and well, so compared to the first two, it has a higher ductility. Of course lah, by the name ductile, we can understand actually. So this is we can attribute this to the structure. So you have this nodule, and for the gray cast iron you have the flakes. So the flakes has covered more area lah. So the dislocation, if we talk about the dislocation theory, then it it is more favorable for dislocation to move in ductile cast iron because it has less hindrance compare if it is in shape of flakes. It will impede, or it will stop by these flakes. So the sphere has less area, effective area, so the dislocation can move better, and in that hence they have a better ductility. And let's see the last one, malleable cast iron has carbon content and silicon content 2 to 6 carbon, 1 to 1.6 silicon. To produce malleable iron structure, cold white cast iron casting are heated in furnace to dissociate the iron carbide of the white cast iron to graphite and iron. So to produce malleable cast iron, we start with cold white cast iron. So we have the in the very beginning, in the very beginning, in this white cast iron, this white cast iron, which already solidify and cool off. Okay, we use this. We heat again. We heat it up again. Okay, we heat it up again in furnace, and as we have in the white cast iron, we don't have graphite. We don't have graphite. So we, by heating in a furnace, we promote diffusion. We promote diffusion, and this uh, iron carbide, iron carbide is metastable. Okay, so the carbon from the iron carbide, they get together and they form graphites, and the remaining will be thereof iron. Okay, so the graphite in malleable cast iron is in the form of irregular nodular aggregates called rosette. So just now the nodular looks like this, right? And very like a circle or like a nodules, but for malleable cast iron, which we use white cast iron, and we heat in furnace to promote diffusion, it forms, it aggregates, it get together, but it's not as clean as nodule, so it has irregular shape. It has irregular shape. So the heat treatment of white cast iron causes a decomposition of cementite. So the cementite decompose, and the carbon, it form graphite. It form graphite instead of being with iron. So which exists in form of rosette surrounded by a ferrite or pearlite matrix. So depends how much you provide those heat treatment. If you provide sufficiently, okay, they form the rosette, right? So the surrounding will be lack of carbon lah, because the carbon get together already. So the surrounding will be lack of carbon. So the surrounding, if the heat treatment is sufficiently enough, so surrounding will be only ferrite. Only ferrite. Okay, but in moderation, if it is still, leftover of carbon traces, so it will form a perlite lah, in the surrounding. So malleable cast iron. So this is well, the among the application of the malleable cast iron. Of course, it also has good machinability and toughness. This is like similar to ductile cast iron. Only that it is made from the white cast iron. Okay, the rosette shaped graphite made the cast iron ductile. So it's the same principle lah. If you have flakes, you cover more area, you do more, like we can say roadblock lah. We have a longer roadblock. If we aggregate into nodules or this rosette, there is not much hindrance as the dislocation it moves. So okay, that's all actually. That's all about the cast iron. And well, just read the summary. The cast iron contain higher carbon content than steel, of course. Yeah, steel is below 2%. Normally between 2 and 4, or more than 2 and 4. Carbon as well as silicon. For cast iron, most of the carbon exists in graphite form rather than combined with iron as cementite. Gray, ductile, malleable. The three most widely used cast iron. The latter two are reasonably ductile. So ductile and malleable, as we know, the graphite shape is round shape or sphere-like or irregular nodule for the malleable. So it is more ductile compared to flakes like gray cast iron. Okay, and white cast iron is the only cast iron that retain carbon in form of iron carbide. So the other form the graphite, but only for white cast iron, because the solidification occurs at fast cooling rate. It has no time to get together to form this graphite. So only for the white cast iron, the carbon remain in form of iron carbide. So this is what I have shown just now. Just a summary of everything today. So you have a a composition of iron and carbon in between these 2 and 4. And if you add magnesium or cerium, right, it will form what we call as ductile cast iron, because the graphite formation will be in form of nodules. Okay, and if the cooling is slow enough, the remaining carbon from the austenite, okay, they will get together to form this, or they will get, combined with the graphite, and the remaining will be only ferrite, And if you don't add any magnesium or cerium, then you will have the option of these three depending on the cooling rate. If it is fast enough, it will not form any graphitic carbon. Rather, it will form this cementite. And if you give time and diffusion, opportunity to diffuse, they will form graphite, flake like graphite. If you give more time, you give more energy, you give more opportunity for diffusion, all of the carbon, they will get together in the uh, graphite flakes, and the remaining phase will be only the ferrite. So malleable cast iron, we use this, we use this white cast iron, we reheat and we hold at a certain uh, period of time, okay, and then we cool it off again, and likewise similarly, okay, if it is a bit fast, okay, a bit fast, then we have this pearlitic malleable. And if you provide enough time, enough energy for diffusion, all this carbon inside the cementite in this pearlitic structure, they will combine with the graphite, okay, and will leave only the ferrite. So that is all actually for this week. We only the content is only cast iron, and this is actually enough already for the cast iron. So it's a bit early, but I'm not sure whether we want to do the tutorial today or not. I think we just do next week because the class also next week. So just to align with them. Uh, it's only we have this what you need to remember, okay, in this class, in this 1 hour and I don't know 20 minutes or yeah. So what we need to remember is the name of four cast iron just now, and then we can describe the microstructure. So you need to be able to sketch the microstructure. As a reference, you have to know the phase diagram, the phase diagram. The phase diagram, from the phase diagram, you can predict already the microstructure. You can predict the microstructure. So for all the four uh, cast iron, especially the first two, the 3 and 4, I think it's just technically we change some, like we add some magnesium, or we do some heat treatment. For the malleable, we do some heat treatment from the white cast iron. So the first two, you need to know how to mm, you know draw this microstructure, and the last two, you need to know the final product. You need to know the final product, how it looks like. Okay. So for ductile cast iron, it had nodules, graphite. If for malleable, it have rosette, graphite. So you need to remember all those things and able to sketch the microstructure of different type of cast iron. Okay, describe the mechanical characteristics. So if we have more nodules or the rosette, it will be more ductile, more machinability, higher machinability, and higher toughness, okay, due to the structure, of the graphite, okay, does not occur in flakes but in nodules. So I think that is all that we have for the cast iron. Apa yang ada? Alright. Ada soalan tak masa cast iron? Cast iron ni pendek je. Cast iron ni just one slide je. Ada tak soalan setakat ni?
Ada.
Apa hari-hari?
Tak
ada. Ada. So
Sir,
alright.
about the assignment, sir. About the assignment.
Assignment, okay.
Dia punya patah perkataan berapa, sir?
Free lah. You can. It's for me.
Free.
I can accept lah, but not. Don't be too
Short, sir.
short lah. Okay.
Yes, sir.
Don't be too short lah. Okay.
Yes, sure. Thank you, sir.
Okay. So assignment is on 30 habis. So I think you guys use the remaining time for doing assignment. Tutorial we will do next week lah. We do more lah tutorial sebab last yang kelas 13 dengan 14 pun dia orang saya nak bagi sama lah semua. And we have a remaining I think 40 minutes already. So then nanti you buat dalam pun dah berapa minit kan. Lepas tu I nak explain pun dalam 10 minit tak sempat. Okay, macam ni lah. So the remaining time you use this time now until 9:40 you check this. I think last time we do the phase diagram just separuh jalan baru, but you use this remaining time you try to complete or try to figure out the question, and the next week we go directly to explain the tutorial. Okay?
Okay, sir.
Alright, so that's all for today and this week already. Okay, so see you guys next week, and next week we will have plain carbon and alloyed steel. So I will upload this one. I think I have not uploaded this slide. So okay, see you guys next week.
Thank you, sir.
Alright.
Thank you, sir.